Okay, I want to talk about lighting, solid state lighting, which is actually a very, very important topic for the future of energy. Okay, so I'm sure like you must have heard about energy, renewable energy, generation from sources which are more like sunlight, wind, biofuels. I'm going to talk about energy conservation. How can you actually conserve energy, because you need to do both to save energy to be sustainable in the future. And my presentation is going to be based on LED lighting. So, getting there, my presentation. So we have a center, NSF funded, National Science Foundation funded center known as the Smart Lighting Engineering Research Center. How many people have heard about this center? Only two of them? Okay, it's on the 7th floor of this building. And if you're not been there, whenever you have time, you should come and see us. There were a lot of interesting projects going on in the general area of solid state lighting and smart lighting. So I'll show you some things, some few applications of smart lighting. What basically smart lighting is, and how do we approach and how do we see smart lighting, helping us in the future, in not just energy efficiency, but also for other applications like human health, productivity, communication, and stuff like that. Okay, so let's see. Computers are getting slower by the day. Okay, so what happened here? Multitask.
Think of all the things you can do to make your computer happy.
Okay, there we are. So, my name is Partha. I'm a professor in electrical engineering department, ECSE department, also the deputy director of Smart Lighting Engineering Research Center. And I want to talk about a topic which is a very, very important topic, as I mentioned, for the future of energy conservation. And the title of my talk is Smart Lighting, the era beyond light bulbs, okay? And when I say light bulbs, I'll specifically mention LED bulbs. So these are not LED bulbs yet, but eventually they're going to become LED bulbs very soon. And what's next after that? So that's my focus of my presentation. Feel free to either stop me during the presentation if you want any clarification. If not, I'll keep some time for question and answers, okay? I want to really rush through a few things because I need to cover, I want to show you a lot of fun stuff in the next half an hour. So outline, I'm basically going to talk about beyond illumination. And what does that mean? That means that once you know how to use the LED light bulb for illumination, that means providing illumination, what can you do with that? And why do you need to even think about that? That's the motivation of my presentation. But before I start, I'd like to actually show this chart. Probably have seen this over the internet many times. I borrowed this from Professor Rich Smalley, who died a few years ago. But he had this very powerful slide which I show in every presentation on energy conservation or energy generation. And this kind of shows that the humanity's 10 big problems in the next, 50 years, half a century is going to be energy, okay? And which means that we need to create energy for so many people, which is equivalent to so many number of barrel equivalent oil per day of generation. And to get those kind of numbers, it's a big challenge, it's a grand challenge. So what you do is you not only just generate a lot of new energy from energy sources like tar sands, clean coal, biofuel. These are very, very new topics of research and technology development going on these days. But also from sources like photovoltaics and wind. Today I'm going to focus on energy conservation. That means how to use solid state lighting for saving energy, but that's also required. We need to solve this problem from different, by using different solutions, and so solid state lighting provides the opportunity to conserve a lot of energy. I'll show you some data which shows the significant impact of solid state lighting. Okay. So let's actually start off with something which is very important to look at when you start looking at new light sources, and that's the spectrum of light. So when we actually talk about smart lighting, and I said beyond illumination, we also need to look at how can we benefit from lighting. And if you are to understand how light benefits us, we need to look at one primary ingredient of light, which is the spectrum of the light. So to give you an overview, a quick overview, this is the sun, and the sunlight has a black body spectrum, which means it has got wavelength across the visible range, in the ultraviolet range as well as infrared range. So human eyes are, they can see only the visible range, which is shown here in the electromagnetic spectrum, a very small part, which is between blue and red. And human eyes are more sensitive to the green region of the spectrum. But the typical black body spectrum for the sunlight is shown here, which goes all the way from ultraviolet light here to infrared light. And the visible part is only around here. Now this is known as a full spectrum light because all the wavelengths of light in the visible spectrum is present in the light source, which is the sunlight here. Then actually incandescent lamps, the Edison light bulb, the candle light, oil lamps, they're also full spectrum light sources because those are also black body radiators. And if you look at the spectrum, this is kind of a typical spectrum of candle lamp. This curve here, this is a tungsten lamp, and the light bulb that you see here, which you have been using for almost 100 years, Edison light bulb, and this is the sunlight spectrum here, okay? But what I want to point out is that this is a very beautiful lamp. It's a full spectrum lamp, okay? But the problem with this is it's very energy inefficient. And the reason because if you look at the spectrum here, the black body spectrum curves that you see here, majority of the radiation that is coming out of this lamp is in the infrared region, which is invisible to the human eye. So that's basically heat. Only a small part of this spectrum is in the visible range, which is light. So whatever we are getting from these lamps, only a small fraction of that is visible light, the rest is all heat. And heat is basically a waste of energy, so we don't need that. We need the light bulb to be sending us heat and not sending us light and not heat. So that's why these are inefficient light bulbs. So people actually developed over the last 50 years fluorescent lamps, which you can see everywhere. This is known as a linear fluorescent lamp, this rod light thing which you see in the corridors, in the buildings. And this is what these days, a lot of people buy this. In fact, I have a lot of CFLs, this is known as compact fluorescent lamp. Go to Home Depot, you can see these. These are quite energy efficient, okay? And I'll show you some numbers that I picked up this morning while preparing for this presentation. So these are very efficient, but they are spectrum deficient. What do I mean by that? If you look at the typical spectrum of this lamp, it has got a small blue line, a little bit of like green, some amount of yellowish green, and a little bit of red here. So this is a very narrow spectrum lamp, which means that it mixes these photons to create white light. But basically it is deficient in spectrum. That means it has got some serious issues when it comes to human health and other things. And not even talking about mercury, right? So let's say when this lamp burns off, you do a landfill, you have a lot of mercury that is getting into the land where you dispose this lamp. But even before that, it has a lot of like issues which are just, people are trying to understand these issues now, and they're understanding that this is really energy efficient but spectrum deficient. So what to look at, so basically if you go and look at, okay, what people advertise these days as full spectrum fluorescent lamps, or they call it artificial sunlight, these have got many more lines, but this spectrum doesn't match either the sunlight spectrum or the incandescent light bulb spectrum, which we have evolved for the last 100 years. So these are energy efficient lamps, but they have some issues with the spectrum. So then comes the LEDs. So LEDs, these are typical devices that you see. The lamp looks very different, and I'll show you a picture of that. With LEDs, the opportunity is that you can not only get very energy efficient lighting, but also you can cover the entire spectrum. So these are examples of spectrum of different lamps, where you can see that the entire visible light spectrum has been covered by what are known as phosphors, which are used for making these LEDs, and they convert the light from blue to different colors. And so you can see that you can get tunable full spectrum as well as you can get energy efficiency. And that's why LEDs are going to be the future of the lamps. Now here is an impact that Department of Energy actually did a study, and they found out these major impacts or these significant impacts if you replace the light bulb, the incandescent light bulb which you have been using for the last 100 years with LED lamps. Okay? I won't have time to go through all these things, but there are three main categories. One is the energy perspective. The second one is the environmental benefit, and the third one is the economic implications. Because you need to look at all these three things holistically to really replace an old technology with a new technology. So if you look at all these numbers, you can see that the LEDs are going to be around 200 lumens per watt. I'll tell you exactly what this number actually means in the next slide. But basically, they are very efficient that you can, if you replace the light bulbs today that we have with LED light bulbs, you can save up to 1 million barrels of oil per year, and also it alleviates the need for 250 nuclear power plants. So there's a huge amount of energy saving that you can see. Environmental benefits, they are tremendous. You can reduce CO2 emission by 952 metric tons per year. Also sulfur dioxide emission can reduce, and the most important thing is that you don't actually dump in mercury into the landfill that is used in CFL these days. Economic implications, again significant. It's an $8.5 billion industry and it's growing at a rate of 8%. So there are significant impacts that you have for all these three categories: energy efficiency, environmental benefit, as well as economic implication. If you go to the DOE website, you can read more about it. So you can see this, which are current pasted from DOE website. You can see how much actually it is already making an impact today when people are replacing the LED lamps with replacing the incandescent lamps with the LED lamps. Okay, so this morning I did a quick math. Okay, so I went to the Home Depot website and said, okay, well, let's actually see how much we're going to pay for this new lighting, the solid state lighting based on LED lamps. So here are three pictures. This is your Edison light bulb, this is your CFL, and here is how the LED lamps look like if you go to Home Depot. And there are many different shapes and sizes, but this is one of them. And without actually going too much with too much of details, because we don't have time here, what I did was actually I took a 60-watt lamp that we are used to using incandescent light. Well, the key thing is the lumens. How much amount of light do you get from this 60-watt lamp? It's around 860 lumens. So if you pick up a lamp which is similar intensity, a CFL of 900 lumens and a LED of 800 lumens, you can see that immediately that the LED is the most efficient. It consumes only 9.5 watts of electrical power as opposed to 60 watts for the incandescent lamp and 30 watts for the CFL. So you can calculate how much lumens you are getting per electrical watt for these things, this lamp here. The second category is the number of hours it operates. A typical incandescent light bulb operates or 60 watt will burn out in 1,000 hours. If you use a CFL, it can last for 10,000 hours, even though it kind of dims down the time. And if you use an LED light bulb, they are advertising at 25,000 hours, which is equivalent to like around 22 years of without changing a lamp if you operate for 3 to 4 hours every day. Okay, that's the kind of number. So the bottom line is, okay, well, why aren't the consumers really going and buying the LED lamps when they're buying the new lamps? Okay, so the reason is because they're very expensive still, because technology is pretty new. So if you want to buy like one particular LED lamp, it's around like $12.50 for each lamp, whereas an incandescent lamp I can buy for 43 cents for the similar amount of power. So I did a little bit of math and said, okay, let's actually calculate how much do you save on the electricity cost every year for 22 years. So if I do that math, and also assuming taking into factor that I need to buy like 25 of these lamps in 22 years compared to just one lamp of LED. If we do all that math, I come with a lumens per dollar, which is basically important for the consumers, right? You look at like how much money I'm paying for the lumens that I'm getting. And looks like I'm getting around 21 lumens per dollar today with LED lamp, 23 lumens per dollar for the CFL, whereas for incandescent it's only 4.9 lumens per dollar. So in fact, this is very attractive, because the fact that I'm just paying $1.50 for each lamp instead of like investing $12 for each lamp. So that's why this is very, very popular today, but this price is coming down rapidly, so that we're going to approach the CFL, and of course then everything is going to get replaced by LED lamps. Okay, makes sense? So now actually there is a huge problem. So this actually is a very interesting historical problem. So when you create a very efficient technology, there is economic implication, and that's very significant. And if you look at the history of incandescent light bulb development, in fact, actually early 1900s when the light bulbs were getting developed, the lamp that burns out in 1,000 hours, that actually could last for 10,000 hours, even 20,000 hours, or 100,000 hours. In fact, there is a place in California there where a light bulb is still glowing for 100 years. Okay. So what happened is that if you look at the historical story in Europe, there are three big companies, Philips, Osram, and Legrand in France. They actually sat together and they did a cartel. They said, okay, well, we need to make the technology very, very inefficient for the cause that like consumer will buy, but still it will burn out and things like that. And engineers really worked hard to make an inefficient light bulb that we buy today. So the 1,000 hours is not an upper limit for the technology. Okay. It's basically designed to burn out in 1,000 hours. So that's actually by design. So engineers have made that inefficient so that they can sell more to the consumers. With the LED, that is not going to work out. Chinese companies, there are like 3,000 of them. They're already making efficient light bulbs which are going to sell for very cheap price and also very low, very energy efficient. It's going to last 22 years. So for every commercial companies like Philips, Osram, and all the lighting companies, the major thing is what is known as the socket saturation. That means when all the lamps have been replaced by LED light bulb, guess what? They're not going to sell any more lamps, right? For 22 years, nobody is going to change the lamp. So what's the problem? What can you do with those lamps? So our center is looking at what is called the second wave of solid-state lighting. So we call the replacement paradigm where you replace the Edison light bulb with the LED light bulb with the first wave technology. So we call it the first wave bulb. And that actually going to solve this problem of socket saturation by what is known as the second wave technology. So that's what is the smart lighting all about. So socket saturation is a problem, is a concern for the industry, and we are looking at technologies which can keep the LEDs, doing more than what it is supposed to be doing. And that is actually basically beyond illumination, and that's basically my talk. Okay. So quickly looking at some basics. So LEDs can do much more. So incandescent light bulbs or CFL can only give you power because light, because it can only consume electrical power and give you light. But LEDs, you can do a lot more with LEDs. You can modulate the LEDs very fast, so you can send data. Okay. You can change the polarization of the light, so you can do many more other interesting things. I will show you one application of that if I get time. You can change the emission profile, that means you can direct the light in different direction. You can mix color to get different white shades of white and things like that. So you can do much more with LEDs. So that is what we are going to be harvesting when we start designing smart lighting systems, because you need to know that this device is much more powerful. There is many more characteristics that you can leverage compared to what your typical light bulb does. And so we actually thought about this idea many years back when we wrote the proposal for the Engineering Research Center. We said, okay, well, look at the vacuum tube. It became a transistor, discrete device, became IC, and then now what we have. And we want to actually follow the same path in photonics, which is basically a light bulb which is replaced by a LED lamp, and then we are going to mix all the complex functionalities of the LEDs to design systems which are going to do much more than that. And I'm going to show you just a couple of examples of what these question marks are here. Okay, what kind of systems are we envisioning with these concepts? Okay, I'm going to skip through all of this because this is our history, transistors becoming a radio in 10 years, and then half a century later, we have all these things in our hands right now. And that is all based on a discrete device, which is a transistor. So we want to do the same thing with LED. That's the vision, okay? Now today, when you look at LEDs, they are used only for two applications. One is for illumination, the light bulb. You illuminate the space, or you display. So you see all the LEDs on the traffic lights, on the cars, on billboards, everywhere. It's used for illumination and display. What's the future? The future is much more than illumination and display. So people are already thinking about things like therapeutic lighting. How can you use light for therapeutic applications? I'll show you one example of a project that I did with the capstone design students at RPI a few years ago. Now it's a real system in St. Peter's Hospital in Albany. I'll just quickly show that therapeutic lighting. Sky lighting is becoming very important, like indoor, this is an indoor beach in Japan. Okay, so this is all based on solid-state lighting displays and LEDs. Adaptive lighting, so these kind of applications already becoming very popular. Mood lighting, most of the new aircrafts, they're having this mood lighting in the cabin to have better relaxation for the people who are traveling, and also like mood lighting is very important in the hotel industry. And then there's something very important called circadian lighting. Okay, and I'll talk about that a little bit more. So the spectrum demand for each of these applications is different. So whatever you do for energy efficiency is not the same as adaptive lighting, and it's not the same as display technology, and it's not the same as human health. So that's why solid-state lighting really helps getting to serve all these applications with the device that we have. Okay, so first of all, let's talk about light and health. It's a very, very important topic because a lot of money is spent in healthcare in US these days because people become ill, and also like it affects the productivity of workers in the workplace. So how can you solve that? To understand the impact of lighting, most of us actually spend most of our time indoors. And if you are flooded with artificial lights, we are missing on many things, including vitamin D. Okay, so we don't go outdoors, we don't sit in the sun, we don't take a walk. So basically that's a problem. So we want to solve that problem by using solid-state lighting, which has got a full spectrum. And also to understand that a little bit more, we need to look at not just the visual system, the eyes, what the eyes is looking at, but also what is sort of the circadian system. We have a circadian system, which is an invisible component that we have in the nerves, which actually looks at the light spectrum, and it does much more than just seeing objects. It also actually decides when are we going to sleep, when can we wake up, and things like that. So circadian system is also very, very important to take care, and that requires understanding how our human body responds to light. And that has got significant impact on cognition, memory, recovery, and things like that. And also human beings interact with light in many different ways, and so basically that impacts our cognitive psycho-physiological health. So that's very, very important, and a lot of medical research is going on trying to understand that. So solid-state lighting provides a good opportunity to address the issue of human health. So in terms of what is smart lighting, it's what we call the smart lighting is the second wave of lighting, where electric lighting is going to become electronic lighting, and you can do a lot more than what lighting can do. We can deliver data with illumination, we can do biochemical sensing, we can do circadian lighting, we can do also adaptive lighting, which will automatically self-commission instead of like us trying to switch on and off the light. So there are many different applications that we can do. Let me actually show you a bunch of examples. So first one is the visible light communication. So we can actually, if we had LED lamps in this room, we can get all our wireless data using the LEDs, because LEDs can switch on and off very fast at a very high speed. So basically you can feed all your Ethernet cable to the light, and then you can get a lot more data, and it's not going to be bandwidth limited. Right now actually all of us start using the Wi-Fi, it gets very slow. With LED lights, you can actually really solve that problem. So that's known as visible light communication. That's one of the applications we are looking at, how to actually get very high efficiency LEDs which can also do data communication and lighting at the same time, because that's important for us. We don't want to make LEDs just for data communication, okay? We want to make it for lighting and data communication. So that's one of the examples. The second one is actually biochemical sensing. So let's say this room has got a lot of bugs, we know that, but we cannot see that. So the spectrum that bugs can be detected, we can do what is known as sensing and mitigation. That means you not only sense, but let's say when this room is empty, it can have certain spectrum, we can kill the bugs. So looking at those applications as well. So we call these as dual usage paradigm. That means we are using the light not just for illumination, but also for doing other things apart from illumination. And the first one was data communication, the second one is biochemical sensing and mitigation. Okay. So how do we actually design this system? We are engineers, we know these are very important applications. How do we design this smart lighting system? So here is actually a holistic view. So there is a three-legged stool approach. So what we do is that we take the photonic source, in this case which is the LED with different spectrum. We also need to have a lot of photonic sensors which can sense the light and provide a signal which is a feedback signal into a control system, which will then actually do the will serve with a control algorithm to then actually turn on the lights depending upon what's needed for whatever application. So it's basically a feedback loop from a LED light source to a sensor, which is basically a mobile sensor or fixed sensor. So we can all be roaming around with our mobile sensors, or it could be on the laptop, on the desk, or whatever that is. And then we need to have a central control algorithm which will actually make the light and the sensor and the user interact with each other. So basically, if somebody asked, a few years ago, somebody asked me to talk because what's smart lighting? So the smart lighting is nothing but the right light where and when you need it. So right light meaning that it has the right spectrum, the data, the polarizability of the light, everything is there, and whenever you need it and when you need it, it will deliver the functionality as well as the energy efficiency aspects of the lighting. That's the smart lighting system that we are developing for different applications. I'm going to just quickly skip this one because this talks about the technological barriers that we have, because that's what drives our fundamental research in each of these areas. And this shows exactly what kind of research is going on in our center. So if anybody is interested, they can go to our website and look at it. There are a lot of different research areas, and we've got these 3 planes which are typical for energy, for engineering research centers, where we have fundamental research, then enabling technologies and engineered systems, ultimately taking us to systems that we anticipate to be useful for the commercial world. Okay, I want to show you snapshots of research that is happening in our center, which is very important and cutting edge and first of the kind demonstrations. The first one is actually what is known as an LEIC. So you have heard about ICs, right? Integrated circuit. So we are developing what is an LEIC, light emitting ICs, which basically is integration of LEDs with microelectronics chips on the same device. And so that actually is very important because that will not only bring down the power consumption of the LEDs when they are doing this dual functionality, but also it will help us get high-speed LEDs and lighting at the same time. We can also get very smart logic systems which can do much more than what the LEDs can do today. So that's the next thing. We also actually work on very interesting materials like nanowires and polarized LEDs which can provide different polarization of light, which is not possible with common light source. Full spectrum lighting, which is using different kind of ceramics or phosphors, which provides the entire sunlight spectrum. So this is an example of a full spectrum light that we have developed in our center using transparent substrates or phosphors. Also, we're doing a lot of work in the area of color science. So color science is actually very important because that provides the perception of objects when illumination is provided to any space. And so we are looking at what kind of spectrum provides what kind of perception, and that's basically, we can get all the way from very high fidelity to high dulling and high saturation. So these are very important topics based on what we can do with these LEDs. High-speed LEDs, as I mentioned, is one of them, and we are designing not only the high-speed device, but also high-speed circuits that can drive the LED to provide data. We're also developing sensors which can detect different wavelengths of light and then do the job for controlling the light as needed. And finally, architecture. So we need to have very smart controls algorithm. So this is actually done in Hollywood quite a lot. I mean, when Hollywood take pictures, they actually does a very interesting job managing the photons coming from different directions. We are kind of actually adopting those kind of solutions in a much more economic way, because Hollywood has a lot of money to implement those kind of things. We cannot do that. So we're trying to learn those algorithms and use it for smart lighting, so we can use those algorithms for simple lighting and save energy as well as do whatever we want to do with the lighting. And then actually I want to talk about a topic which is very near and dear to me, which is lighting and display fusion. So display meaning the display which is a screen, a laptop screen, a big display, a TV screen, that's what is display. Okay? Lighting is illumination. So if you merge these two systems, it's known as lighting display fusion. So I'll tell you about one application where it makes a lot of sense and it has a huge impact. So let's talk about ICU, intensive care units. So right now actually, if you go to an intensive care unit in a hospital, it looks like this, okay? And there's a major problem with the patients who recovers in these ICUs today. They have things like delirium. They get confusion, they come back again. And so trying to actually understand the reason for those kind of issues, they have found out that when patients are recovering in ICUs, since they don't have any orientation of the external world, they get confused when they get out of the hospital. Okay, and that leads to a lot of healthcare increase in healthcare costs and things like that, and also inconvenience for the patients and things like that, and also there's mortality rate which is increasing. Okay, so to solve that problem, people have started actually using what's known as skylighting solutions. You can see here on the top of the on the ceiling, they start putting like these LCD screens which will show like clouds moving through the thing, and then it appears as though you're sitting like below the sky. But this is actually highly inefficient, plus the patients don't have much benefit from this one because it's just a display. So the future of ICU is going to something look like this, where there's going to be what's called a virtual window, which will basically orient you with the external world. And here is actually a project which is real. Okay, so this is a project which we did at RTI, undergraduate capsule design project. I was leading this project, and we actually built a system which have been installed in fall of 2012. This actually collecting data with patients. These are actually virtual windows where there are LEDs behind, so there is no hole in this wall. And this is actually a camera which provides the outdoor real image of the parking lot and cars moving around. And this is actually, you can go to St. Peter's Hospital, 22 rooms are already fitted with these kind of windows. And so this is actually what we call as the lighting display fusion system, and this is actually a therapeutic window system which not only helps orientation but also helps with therapeutic purpose for the patients. So I hope I've given you enough views about what is smart lighting and what are systems to anticipate. I'm running out of time. I'll stop here and take questions. How about that? Okay. Thank you for your time. Yeah.
How about rather than virtual depictions of real life, ways of diverting natural light into rooms? Are there any systems like that?
Yeah, I mean there are many solutions, but again you need to think about the economics of this solution. So you need to meet certain economics. So within the bounds of whatever economically it is possible, whatever we are developing, those will meet the economics of the end consumer. That's very important. But yeah, to answer your question, yes, there are a lot of solutions which can bring in light from outdoor, but to make holes inside the walls of a building is much more expensive than putting a virtual window inside. Yeah.
Could those ICU screens also be used to do diagnostic medicine? So if the patient crashes, they can also display X-rays or
yeah. So that's actually a very, very interesting topic. Okay, so you don't want the patients to feel that that's actually a fake display.
Right.
Okay, so what happens and they'll not record. So we are trying to play around with the cognition, human cognition, right? So in those ICU, if you go and see, they have a separate TV and they have separate display, which is a window. So people ask, okay, why don't you have the TV there? Well, then that's going to serve as a therapeutic, window. So basically, you need to understand what's the purpose of that display.
Right.
So you don't have to show that, oh, this is the baseball is going on in the evening, and then in the morning you see the parking lot. That's not going to serve the purpose. So there's a special display with a TV for the baseball game, and then that window which shows day and night as it is outside. And that the purpose of that window is orientation, which will help in your cognition and psycho-physiological improvement.
Okay, I was thinking like if the patient was unconscious or something,
Yeah.
whether you could switch on an emergency for that.
Yeah.
That's interesting.
You need to talk to the lawyers and the doctor at the same time, so liability issues. Yeah, but yeah, there are multiple purposes that one can do. In fact, actually, when we were doing the project, first of all, we said, okay, well, why don't you actually make the patient recover by showing the beautiful beaches of Hawaii or whichever place they like a snow-covered mountain in Aspen. But then actually the lawyers came and said, well, if somebody actually is watching Hawaii right now and then they get discharged and they go and see like downtown Albany and they get depressed, then they want to come and sue the hospital. So we decided to actually put the camera and take the real image, which is live image that gets fed into these displays. So there are other issues of technology implementation, not just the engineering aspect, but also the legal aspects and other things. Yeah.
So if you were to have like the internet communication through smart lighting systems and stuff, would there be any like energy savings versus energy price savings versus separate systems, or would you be able to get better price performance and energy with the combined smart savings?
It's a very, very good question. So right actually, most of the energy consumption for the Wi-Fi takes place where they have the towers, right? There's a huge, a lot of power is consumed there. So with the lighting, you're not going to actually consume extra power. It's basically a net zero power budget. So you're not going to actually increase the overall power consumption of the LED when you start doing data communication. So that's basically much more energy efficient. So to answer your question, yes, Li-Fi, which is basically light-fi, is going to be much more energy efficient than Wi-Fi. Yeah. But there's one challenge, probably you guys didn't get it, okay? Wi-Fi can penetrate through doors and walls, right? But Li-Fi is going to be like line of sight. So you need to sit below the light to get your data. So you walk out, you're going to get your data from here.
Can you communicate with multiple devices?
Yeah, yeah.
How about that?
Yeah, basically actually whatever the light is, you can sit like 1,000 devices here and get the same data. That helps the bandwidth, solution. You're not going to be limited by your bandwidth. The bandwidth, like right now, you have with Wi-Fi.
But could you also do like different frequencies so that different devices can be communicating with different
Yep.
channels?
Modulation.
Yeah. Multiplexing, yes.
Yeah.
You have a question?
I was just about to ask about that. I was going to ask whether there was enough wavelength that we could utilize with time division multiplexing or frequency multiplexing to actually have that kind of communication, say, throughout this room with a really smart building. And also as a follow-up, it seems like a great idea as one-way communication, but
how do you do the uplink? Okay, so downlink is very easy. How do you uplink, right? That's the question we get asked every day. Whenever we demonstrate this to like people like Cisco or Qualcomm or of the world. Okay, so basically downlink is very easy. So to uplink, you need to have infrared LED. I mean, there are many different solutions. What we are figuring out, we can have an IR LED which will communicate with the sensor in the lamp. So the smart lighting lamps are not just the lamps, they will have sensor embedded into the lamp. Okay, so when you do uplink, you're basically sending with your LED, pointing up the data to the lamp, and from there you have an Ethernet cable which will take the data out there. Okay, so you basically have a sensor in the lamp to do the uplink. And in terms of the protocols, like people are actually developing same protocols like the OFDM, orthogonal frequency division multiplexing, that they use for Wi-Fi. Even for the Wi-Fi. So people are just doing the parallel, IEEE is coming up with standards for communication with Wi-Fi in the next few years. Okay, so that's going to happen. It's happening right now. But of course, as you know, that any new technology is not going to just like cruise through with a solution, right? There are also the Wi-Fi people. If you look at the IEEE Spectrum magazine every month, right? They go, Wi-Fi is like never going to work out. Like so, Wi-Fi is improving better and better and better. So there is a lot of competition between different school of thoughts, people, and also different technologies. So it's not going to be an easy cruise through solution, but eventually the data need is becoming so high, data demand is increasing so high that you cannot just do it with Wi-Fi. My kids actually do like homework by doing Skyping every night. So I'm just, they're like sitting with like 4 or 5 people, friends, and like asking, okay, how did you do this? And they're having discussions. I mean, imagine if every kid starts doing their homework by using Skype, then you need a lot of, the data demand is going to increase. So Wi-Fi is not going to have a solution in the end at some point. So Wi-Fi is going to come in. But till that time, Wi-Fi guys will have a good time. Yeah.
I know as the data is emitted and there's changes in the emitted spectrum, it's imperceivable to the human eye, or at least to see the difference in change. But would there be any positive or negative effects by the rapid changing of the frequency?
The answer is no, and that's again a very good question. So what he's asking is that if you send data, you're flickering the light, right? So is human eye going to be seeing that? The answer is no, because it's moving at a very, it's flickering it's modulating at a very high speed. Like we're talking about like 100 megabits per second. Human eye can see only like 500 kilobits per second, right? So you're going to see those modulation, okay? So that's the first thing. Second thing is that the spectrum, we are also looking at the entire spectrum that is getting delivered. So whether the light is coming as a continuous thing, or if you go back to like quantum mechanics, Einstein's like equation equals h nu, actually every light that you are seeing has a fluctuation, right? Already inbuilt in the quantum mechanical like photon concept. So basically what we are seeing is like a semi-continuous, but actually at the photon level it's flickering. Okay, we know that. So there is no like known effect, or people are not actually anticipating any physical or health issues with light which will modulate. But there is a very, very high data rates, very high modulation rates. And you're not going to see anything, flickering or anything like that. It's going to be like a continuous lamp. And we've done a lot of experiments in the lab. If you come up to our center, you can see like the visible light communication where you can't even feel whether it's transmitting data or not. It gets a little bit dimmer because now your duty cycle is deciding how much light is getting averaged, intensity is getting averaged. So that's the only difference you can see.
All right.
Any other questions? Okay, I'm sorry that there was a communication gap between the timing, but I had like 2 more hours of presentation, maybe some other day. Somebody should know what else is going on.
Do you post your slides online?
I could do that.
We can put them up on our private site.
Yeah, I think if it is a password protected, that would be good because
Yeah.
otherwise we've got a lot of competition for.
No, totally understand that. We can put them up on a restricted space.
Okay, I appreciate that, and thank you again for giving me the opportunity to come and talk to you. And if you want to learn more about it, you know my email. Just come and see me or send me an email. I'll be more than happy to share more interesting stuff like this. But do feel to come and visit us when you have time. Thank you very much.